Water freezes at temperatures below 0 degrees Celsius. How does the entropy of water change when it freezes? Does it increase or decrease? It decreases. So the entropy decreases. But is the process spontaneous? Water freezing below 0? Does it happen by itself? Yes?
It does.
If you put water in the freezer, will it freeze? Yeah, it's spontaneous. Now, does this predict that it's spontaneous? No, right? What we've learned so far is that an increase in entropy suggests that something's going to be spontaneous.
Yeah.
And so here, the point of these questions is that there's a contradiction. So the entropy is increasing, but the process is spontaneous. So how do we reconcile that? Well, the second law of thermodynamics says for any spontaneous process, the entropy of what increases? Is it the system? It's the universe, right? So the universe is the system and the surroundings. So the entropy of the universe increases. So when water freezes, the entropy of the system, the water, decreases. It's a spontaneous process. The entropy of the surroundings must be increasing, and they are increasing more than the water decreased in entropy. So we have to distinguish between the system and the surroundings. And we talked about this in Chem 1A, but the system is whatever part of the universe you are studying. And you can define that however you want. You know, if you're talking about something happening to your body, you could talk about your index finger as the system, or your entire body as the system, or your nose, or, whatever. So we can talk about water in the freezer being the system. We could talk about the entire contents of the freezer being the system. Whatever is not the system is the surroundings. Oftentimes we're only looking at the nearby surroundings, but technically it includes the rest of the universe. So we've got the system, the change in entropy for the system, the water freezing, and we have the change in entropy for the surroundings. We add those together and we get the change in entropy for the universe. So the entropy of the system can decrease as long as the entropy of the surroundings increases more. So why does the freezing of water increase the entropy of the surroundings? Freezing is exothermic. This is not something that just makes intuitive sense, right? When I think of an exothermic process, I think of something giving off heat, like the combustion of natural gas in a Bunsen burner. Exothermic process, right? It gets hot, you don't want to touch it, right? Exothermic process. But water freezing isn't hot. Sometimes it's helpful to look at the opposite. Water freezing, water melting. So ice melting, if we want to make that go faster, do we add heat to it or take heat away? We add heat to make the ice melt faster. When the ice is melting, that's an endothermic process. That means the reverse has to be an exothermic process. It's not something that's intuitive. But freezing, the way you get things to freeze is you're pulling heat out of them. And that's what the freezer does, is it's pulling heat out of the inside of the freezer. Entropy is the dispersal of energy. So as freezing occurs, energy is released into the surroundings. Entropy is the dispersal of energy. So release of the energy into the surroundings increases the entropy of the surroundings. So here we have the entropy of the system. The water freezing is going down, is becoming more ordered. Its energy is more concentrated. The entropy of the surroundings, though, is increasing. And when we add these together, we get a net positive change in entropy for the universe. You follow that? Does that make sense? Yeah.
So is one always going to be negative and the other positive?
Good question. Is one always negative and one always positive? No. Sometimes they're both the same sign. Yeah. Any other questions?
But one is always going down and one is always decreasing and it's always increasing.
That's a good question. Is there always one that's decreasing and one that's increasing? I don't think so, because entropy is not a fixed quantity. Entropy is not conserved like energy. In an energy exchange, there has to be one gaining and one losing. In entropy, the entropy of the universe is just increasing all the time. Basically, everything's just becoming a big jumbled mess, right? So, excellent question. But the sum of these can be either positive or negative. Yeah.
Is it like relative depending on like the system you define or whatever?
That's a good question. Is it relative depending on the system we define? So, how am I losing myself here? The amount of entropy change is going to depend on the amount of stuff. So how big, how much water are we talking about? That's going to change the amount. But that's also going to change the change. It's going to affect the change for the surroundings as well. So yeah, there's definitely a lot of possibilities in here, depending on how you define things. But the bottom line is that the entropy of the universe increasing means we have a spontaneous process. That's the one I thought I was looking at. Okay, so we do know that the freezing of water is not spontaneous at all temperatures, right? So the magnitude of delta S for the surroundings is going to depend on the temperature. So it's not only, the size of the system, but it's the temperature at which this is happening. So the greater the temperature, the smaller the increase in entropy for a given amount of energy being dispersed. Well, why is that? Because delta S equals Q divided by T. It's energy dispersal per unit of temperature. So if the temperature is big, then taking a fixed amount of energy dividing by a large temperature is going to give us a small change in entropy. If the temperature is small, taking that same amount of energy dividing by a smaller temperature is going to give us a larger delta S. Does that make sense? So delta S is dependent on temperature. So, and that's because it's joules per Kelvin. So looking at the process of ice or water freezing, the entropy of the system is going to be negative for that, the change in entropy, because freezing of water is an exothermic process all the time, right? And so energy is going into the surroundings, the entropy of the surroundings is increasing. I'm sorry, the energy of the system is increasing because it is losing energy. Delta S for the surroundings is going to be positive, but the size of it is going to change depending on the temperature. So it could be large or small depending on the temperature. So here we have one thing being negative and the other thing being positive, and the sum of this being positive or negative depends on how big this one is, depends on the temperature. Yeah.
So would that mean like in colder environments that there would be a higher level of entropy because there's a lower temperature?
So at a low temperature, the amount of energy is divided by a smaller number, and so the change in entropy is larger than for the same amount of energy being distributed at a high temperature. Yeah. And so what we see here for water freezing is at a low temperature, well, the change in entropy for the system is the same, both at a low temperature and at a high temperature, and it's negative. But the entropy change for the surroundings depends on the temperature. So at a low temperature, this entropy change is larger, and at a high temperature, it is smaller. So at high temperatures, we see that the sum of these is negative, that the entropy of the universe would be decreasing. That would be non-spontaneous. At a low temperature, the entropy of the universe is increasing, and that's a spontaneous process. And we all understand that water freezes. Water freezes when it's cold. Water doesn't freeze when it's warm, right? It's only supposed to be 77 degrees today. Awesome. But is water on the sidewalk going to freeze today? No. It's just not going to happen. Well, what if it was zero Fahrenheit outside? Would water on the sidewalk freeze? Yeah, it would. Because it's colder. But why? The entropy. So the entropy of the surroundings is going to depend on the temperature, and so then the overall sum, the overall change for the universe can be positive or negative. Yeah.
Were both of these examples of exothermic reactions?
Yes, both of these, it's the same process, water freezing. So water freezing is exothermic, and that's why the change in entropy for this system, heat is going out from it, and it is becoming more ordered, and so it has a negative entropy change. And so just based on that, we do not expect water to freeze, ever. But we have to consider the entropy change in the surrounding, and that heat going out into the surroundings, a dispersal of energy, is going to be a positive change in entropy. But the overall change for the universe depends on the relative size of those things. And so at low temperatures, the change is positive, and at high temperatures, it's negative. Water doesn't freeze at high temperatures. It freezes at low temperatures. Yeah.
Is there ever a condition where, well, I'm trying to see if, what is the definition of spontaneity?
We're getting there. Yeah, we're getting there. You're trying to piece out, well, what does this mean for spontaneity? We're getting there. Any other questions? So when the system exchanges heat with the surroundings, it changes the entropy of the surroundings. So we can use Q-sys to quantify the change in entropy for the surroundings at constant pressure. So Q-sys is the energy for the system, right? And so for the surroundings, its change in entropy is going to be opposite from the direction of the heat from the system, right? So if the system is changing in an exothermic way, it's putting energy into the surroundings getting energy is being dispersed means a negative change in entropy. So change in entropy for the surroundings is proportional to negative Q-sys. The magnitude of that entropy change is inversely proportional to the temperature. So delta S for the surroundings is proportional to 1 over T. So we can combine those two things together. Delta S for the surroundings is equal to negative Q for the system divided by T. So if we have constant temperature and pressure, we learned in Chem 1A, at constant temperature and pressure, delta H is equal to Q, the heat exchanged. So delta S for the surroundings, change in entropy for the surroundings, is equal to negative change in enthalpy for the system divided by T, assuming that things are constant pressure and temperature. Questions? Okay, let's look at the reaction between nitrogen and oxygen gases to form dinitrogen monoxide gas. Calculate the entropy change in the surroundings associated with this reaction occurring at 25 degrees Celsius. So we just learned that the change in entropy for the surroundings is equal to negative delta H for the system divided by the temperature. So delta S for the surroundings is equal to negative delta H for the system divided by the temperature. Well, they gave us delta H, 163.2 kilojoules. So 163.2, instead of kilojoules, instead of kilo, I'm going to write what it means, times 10 to the 3 joules. That's not proper scientific notation. Your calculator doesn't care. And then we're going to divide by the temperature in Kelvin. 25 plus 273 is 298 Kelvin. And there's this negative sign here. Let's just call that negative 548. The entropy change for the surroundings is negative. This indicates an endothermic process, right? Energy is going into the system. Energy is coming out of the surroundings. And so the change in entropy for the surroundings is going to be negative. What's the sign of the entropy change for the system? Is it positive? That's a great question. Well, how can we think about it? Well, we can look at the chemical equation here and see what's going on with the states. Here we have 2 moles of gas and 1 mole of gas. A total of 3 moles of gas are becoming 2 moles of gas. So when you have fewer moles of gas, you have lower entropy, right? So the sign of the entropy change for the system is also negative.